So this is lecture 1, continued at first. Okay, so remember that we had an example. So there was an example and we wrote the resolution. So we got a resolution. This is abbreviation for resolution. We got a resolution that looked like S shifted, not at all. You could put S of 0 if you want. So S not shifted. And this was resolving S, which was K of XY mod X cubed XY. Okay, so then the first map, the kernel is just the ideal X cubed XY. So here we had, and if we wrote the shifts in, we had a shift of -3, direct sum, a shift of -2. I'm just putting them on top of each other because it's more space saving horizontally. But it's two basis vectors. We called them E1 and E2. E1 went to X cubed. E2 went to XY. That's why this was shifted by 3 and this by 2. So this matrix was X cubed in the first column. That's the image of the first basis vector. The second column is the image of the second basis vector, was XY. And then there was one more map. If we took the kernel of this, it was generated by the vector -yx squared, right? So you could think of that as that times E1 and that times E2 in here. And that was the only thing in the generating the kernel. So you just get S. And how much was that is that shifted by? -4. So the quick -4, the quick way to think about that is, look what you have so far, -3 here. And the part of this that lands in the first guy is the -y. It's degree 1. So now this was -3, so it just got 1 worse. That's the best you can do, a linear, because this is always, these entries are in the maximal ideal for the minimal resolution. So the best you can do is that it has degree 1. That's the smallest degree, and then it shifts by 1. If it has degree 2, the -2 shifted by -2, and it's also in -4. This has to match. This will always match. This will always. That's a theorem. Okay, and this ended. Did someone say something? Good? Okay. All right, so we got this resolution. And so what I want to talk about in the first part here was what I didn't get to was how to write this information in something called a Betti table. So Betti tables. So I'm just going to write the shifts and the ranks more conveniently in a table. Okay, and this table can be obtained on the computer algebra program, Macaulay 2, which I told you on the first worksheet at the bottom how to access if you want. And it's very easy to run. So you should try it if you have it. Okay, so we're going to, first we're going to write these graded. Let me remind you what the graded Betti numbers are. So we write Fi, each free module, as a direct sum of S shifted by -j. And you might have several copies. So beta I, so for the ith F, J for the jth shift, records what rank it has of that shift. And this is all over all J. I mean, if the module had some negative degrees, you might, I'm not going to write what J has to be. Normally J is positive, so that minus J is negative. But if you started with something that was generated in negative degrees, it wouldn't be, or positive degrees, negative degrees. I'm not going to write it, okay? So anyway, and so in these ranks, beta ij, I told you were called the graded Betti numbers. Okay, so we just want to look at all those ranks. So for example, here there's one thing shifted by 0 in F0. Right, so this module right here is F0. This one was the free module F1. This one was the free module F2. Okay, so we're just going to write in each part how many there are of each shift. Well, there's only one of each of the ones that are here. And okay, so this is the first attempt, which is not quite the most compact way to write it. So this is not actually what we're going to do, but it's almost what we're going to do. Okay, the first attempt is to make a chart where, let me put a diagonal line here, where I is, these are I values, 0, 1, 2, 3, whatever. And these are J values, the shifts, 0, 1, 2, and so on. Dot, dot, dot. And in the ijth place, whatever, I over and j down, you write beta ij, okay? That's not going to be as efficient as we want. We're going to move things around a little, but it's almost the right thing. I still want to write this one first. Okay, even if, oh, I think I can just keep going here. Okay, so let's do that for this. Okay, so for this example, if we just write I and j, I could be 0, 1, or 2. So that corresponds to F0, F1, and F2. Right, so 0 is for F0, 1 is for F1, 2 is for F2. Okay, and then the shifts are 0, 1, 2, well, 3, oh, up to 4. The 4 was the worst shift. Okay, so look at F0. There it is. What shift do we have? Only 0. Okay, how many? What rank does this have? 1. So there's only, in F0, there's only one thing shifted of rank of 0 amount, and there's nothing shifted otherwise, right? You can put zeros, or a lot of people just put a dot. There's nothing there. Okay, look at F1. What are the shifts? 2 and j, 2 and, so it's minus F, it's shifted by minus j. So 2 and 3 are the shifts, right? So we have 1 shifted by 2 and 1 shifted by 3, and everything else is 0. Okay, what about F2? Just have something shifted by 4. So let's put a 4 here, and then zeros above that. Great. So I actually like to also record what the maps went. So if this 3 and 2 thing went by x cubed and xy and landed in this 0 thing. So that was this rank free 1 module and this one too. Most people don't put these arrows in. I just think most people put them in their head. Okay. And so, I mean, this first map, the one that was just from a shift 2 to shift 0 was the xy part, right? So if you really want, you can even write xy. That was exciting, and x cubed. But okay, that's getting a bit too far. And then this 4 from the end lands, and it's a combination of both of these basis vectors. So this guy's basis goes and comes to a combination of those two. So in your head, the resolution has kind of going along like this, right? Good. So now what we're going to do is move it around a bit, but F dot is minimal. We're taking a minimal resolution and writing this. Otherwise, this is not called the Betty table. Okay. What do you know about a minimal resolution? Yes.
This was probably mentioned last time.
Yeah.
I forget, like, how do we know this is minimal?
How do we know this is minimal? So that's exactly going to answer that. Thank you. So someone else, how do we know this is minimal? All the entries are in the maximal ideal. That was one of the equivalent conditions. The other one was that whenever we looked at a kernel, we took a minimal set of generators, but it's equivalent. Okay, so, but that's the one I want. The image of each boundary I map is contained in the maximal ideal times f whatever, I minus 1. Okay, what is the maximal ideal here? It's like, you know, it's the variables, right? X, in that example, it's xy, it's more variables sometimes. So that tells you you have to shift, this can be x, a combination of x and y, or it's in the ideal. It could be higher degree things, right? Like here. So it has to shift by at least 1 if it's in the maximal ideal. Or maybe 2 or 3 if it's x squared or x cubed or something. Okay, so if it's the best you can do it, so it has to shift by at least 1. So at each step, the shifts increase by at least 1, or the thing dies, right? So, great. So that means that for F1, you're never going to get an S0. You're going to get an S minus 1. Okay, so by plus 1, I mean minus 1, whatever. Okay. So you can get an S0. No, you'll never get S0. You'll get S minus 1 or minus 2 or minus 3 and so on. So S0 will never show up in the 0 column. So this guy right here will never happen, right? Okay. In the next one, this has to be shifted by at least one. So you'll get either S minus 1, S2, 3. I mean, we didn't get minus 1, but anyway, you get minus 1, minus 2, minus 3. Now it shifts one more. So it's minus 2, minus 3, minus 4 of some choice of those. It was only 4, but whatever. So this and this will never appear. So just take the picture and shift it up. I mean, as far as possible. Those will never appear. So just shift those columns up. And that is the standard way to write this picture just because it's traditional. It's more compact. You'll never get these, so you might as well just move these up. Okay, don't move everything up. I got 0 here. I'm not getting rid of it. I'm just saying move this column up by 1, this column up by 2, this column up by 3. That's all. Okay, so when you ask Macaulay to do it, that is exactly what Macaulay will do. Okay, so rewriting this one, and I do want to rewrite it because I just want to say one more thing about it, and then I will be done. So rewriting this one. If there are no questions. What you're really doing is writing in this first row still I, so 0, 1, 2, whatever. In this case, it only goes up to 2. So this is F0, F1, and F2. But here, you're not going to put J, you're going to put J minus I values, which is very hard to get your head around, but it really means you shifted everything up. And I'll tell you more about how to think about that in a second. So 0, 1, 2, I don't know, we'll see how far we go. Okay. All right, so let's take that table and shift it. So first you have a 1 and then you have zeros. That one didn't get shifted, the first column. The next column we shift up. So it's 0, 1, 1, 0. Or maybe I'll put a 0, whatever. And the next one is shifted up by 2, so I get 0, 0, 1. So in fact, this part isn't even needed down here. There you go, more compact. But in your head, it's like hard to go J minus I, blah, blah, okay? So let me tell you what we really think when we look at this table. Again, I think of the arrows being the differentials. So from F1 to F0, you have some differentials. From F2 to F1, this is like a free module of this rank, the basis of the basis, okay? And so this map right here, that's going straight across, before you shifted this one by a bunch and this one by even more, it was going this way. It was changing degree by 1 shift, right? The minimum amount, okay? So this here is a degree 1 sort of entry in the matrix shift. Okay, that means this is a linear map, it's called. I mean, the entry in the matrix there will be degree 1 in the matrix. Okay, so the horizontal lines in the picture are linear things. Okay. The things that go 1 row up are quadratic. So this guy here is quadratic. In fact, they are linear and quadratic, right? The y and the x squared. And the things that go up 2, like from here to here, this goes up 2 rows. By the time 2 rows up, this was 2 rows up is degree 3. Degree 3 or a cubic. That was the multiplying by x cubed part. Okay, so just like, so horizontal things are linear. And the really cool thing is that if you look at the very top, well, there isn't anything top here, like if you take some top part and it went, if it was longer and it went over and over and over and over, that's called the linear strand. And it's a subcomplex because the arrows all have to go over or up. And so they stay within there because there's nothing above it. And they can't go down. So it's a subcomplex. If you know stuff about chain complexes, that's a subcomplex and it's famous. It's called the linear strand. And then when you go modulo that, the next set of stuff is a subcomplex in the quotient and it's the next linear strand. I don't know what it's called and so on. So those are things that people study because they tell you stuff. Okay. So I think that's all I want to say about the Betti table. So that, and to summarize, the Betti table will be I, J minus I, and you put beta I, J minus I here. Well, Yeah, and then some people like to rename this as J. I'm not going to do that. I'm going to rename it as J prime. And then this is J prime. No, wait, that's not good. Plus I. Yeah, so maybe I should have just put beta ij here. I don't know what yeah, it should be, so this would be beta ij is kind of what you write, but you write that in the j minus I column. So let's still call it beta ij. And then in that case, j prime is j prime plus I was what j. So j becomes j prime plus I. And then if you rename j prime j, some people write the name the table. They name the embedding numbers beta I, j plus I, but I find that confusing. Okay? I mean, like you don't need to worry about what I just said if you don't want to. It just, if you ever see this and go like, but that doesn't sound like what I learned, that's just re-indexing. Okay?
About the subcomplex.
Yeah. Well, here there isn't really one. So if I had stuff in the first row, they would all be joined by these nice linear maps. But anyway, just because they're in the first row and the arrows all go across, they never go down. That means that this is a subcomplex because the image of the differential stays inside that complex. So therefore, it's a subcomplex, and it's a famous one called the linear strand. And sometimes you don't resolve like S mod I, but you resolve I, which would kind of get rid of this part of the table, and this will be the linear strand. But anyway, yeah, it's just a famous subcomplex. Huh? So it's true for the first row, and then if you mod out, well, yeah, what do you mod out by? I mean, if you mod out by that complex, the next row is a subcomplex. Yeah, and this is not my research, so I don't really know more. So if anyone has comments at some point about it, you are welcome to say. But these are linear strands. And so, for example, over Kazoo algebra, if you're resolving the residue field, there will just be this linear strand. And for other things, you're asking like sometimes how much more is there besides the linear strand. So that a linear strand is also, I mean, it's the diagonal part of the acyclic closure. There's like, this is some of this stuff is intrinsic and important in ways that are not so obvious, because algebras have a duality theory, so somehow, I mean, this doesn't, but the linear strand parts are somehow related to that a bit. Yes. Mm-hmm. In a sense, yeah. So he's asking if you get rid of the linear strand and look at what's left, are you kind of asking how far you are from a linear resolution? Yes. Okay. All right. Oh. Well, I'll just trade the two. Whatever. I'll go over here. Okay, now I'm on to my second lecture, which is actually a very short lecture. And it's just an interlude of a very famous resolution. So these are called Taylor resolutions. And they're very, very pretty. How many of you got to the problems about Kazoo complexes? Okay, good. So some of you know what a Kazoo complex is. This is almost like a Kazoo complex, but it's modified a little bit. Okay. I'm just going to start with an example and then explain it. So this is just S is K of XY, and I want to resolve. So find the minimal free resolution, MFR, of S mod X squared, comma, XY. Okay, so we start. S mod I goes to 0. First matrix has an X squared and an XY, and this is 2. I'm not, okay, I'll put the shifts in. S2, they're both shifted by -2 because these are both quadratics. E1 goes to X squared, E2 goes to XY, and now you want to know what combination goes to 0. You want the kernel. Okay, but I want to be more careful with this. Okay, so let's look at, oh, that's differential one. No, that's, sorry, that's epsilon. 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 So the kernel of epsilon is all the combinations, you know, R1, E1 plus R2, E2, such that R1, so what's epsilon of E1? So apply epsilon to this and I should get 0. X squared, that's what E1 gets mapped to? Yeah. Yes, okay, that's why you're all looking at me. That's why me too, I thought it should be differential 1. Sorry. I skipped a step. S. That's why you're all looking at me. Now the kernel is I. It's generated by x squared and xy. X squared, xy, S2, and I guess they're shifted by -2. Good. So now E1 goes to x squared, E2 goes to xy, and now we want the kernel of that. Sorry, so it's the kernel of, I wrote the wrong thing here, differential 1. Oh, thank you. Thanks. Okay, so R1 times, so apply delta 1 to this. So I get E1 goes to x squared. The other one goes to xy, and I want to know when that combination is 0. So what are the relations here? And I know you know this, but like what, you could probably guess it, but I just want to do it like the beginner way for a second. So let's guess that if I just put in the other guy, xy here, and I put in the x squared here, then they'll cancel and I put a minus sign. So you notice that minus xy times x squared plus x squared times xy equals 0. So I could put minus xy and x squared in. So I just want to mention, well, but what could you do better? Factor out an x. So it's better if we divide by the GCD of the two guys, x squared and xy, so divide by, which is just x, and you'll get a better relation. You'll get minus y times x squared plus x times xy equals 0. And so that's the better relation. Okay, so that means that, so in fact, the kernel will be generated by, let's write it out slowly first, minus y E1 plus x E2. Okay, but I could also write that as a vector. Oh, I'm writing it kind of low. As a vector, minus y x. So that's what it's, oops, generated by that one. Okay, and the first one that I wrote up there is a multiple of it, so I don't need it. Okay, that first one that I wrote is a famous combination. So minus xy e, oh, I'll just start on the next board. It's the board that moves. Minus xy E1 plus x squared E2, which is also in the kernel, but not generating it, is actually the differential of E1 times E2 in the Cazul complex. So if I just went on and wrote the Cazul complex for the rest of this, this is a differential of the product E1, E2. I'm not writing the Cazul complex, but were I to continue and write the Cazul complex right now, which I'm not doing, it would be the differential of that in the, so the differential in the Cazul complex K, differential K. So only differential in the Cazul complex. And so these are called the Cazul cycles. Cycle means something in a kernel. So these are the Cazul ones. But you see, so if I wrote the Cazul complex, that would not be good. That would not be exact. Because the image of the basis of degree 2 in the Cazul complex is hitting this guy. But this is not generating the kernel. So K is not exact the image of boundary 2 is this guy, which I'm now going to write as a column, minus xy x squared. And that's not equal to the kernel of boundary 1, which was minus yx. Okay, so the Kazoo complex is not exact. But if we divide the differentials by some GCDs, it becomes exact. So if we modify the Kazoo complex a little bit, it's exact. Oh wait, I should finish writing the resolution. Here we go. Let's write the resolution over here. So going way back here, I computed this kernel. It was given by the vector minus yx. So that's minus y e1 plus x e2. And that is s in shifted by how much? Minus 3, because it was minus 2 and now linear degree 1, so minus 3. And then it ends with a 0 because the kernel is 0 if you calculate it. So this is almost the Kazoo complex, but this guy has been divided by the GCD of the two things. If I had minus yx and x squared here, it would be the Kazoo complex. As you see, we just computed the differential of the Kazoo complex. It's this. So, but that would not have worked because in fact the kernel is a bit larger. It's image generated by this instead, not x times this. Okay, so Taylor resolutions are essentially the Kazoo complex with some stuff divided, some GCD-like things divided out. Okay, and so in fact, the image of delta 1 is really the Kazoo cycle divided by the GCD of the two things, okay? Dividing, so I'm writing this because dividing by GCD, so you could, the problem is how to continue if you have more stuff. How do you keep going? It's not as so obvious, but if you rewrite dividing by GCD as some kind of LCM stuff that I'm not writing right now, it's easier to continue the resolution, someone saw. So I'm going to not be dividing by GCDs, I'm going to be writing LCMs, but it's in this step, it's the same as taking the LCM of x squared xy divided by the LCM of just like x squared. I'll get a y, that's where the y comes from. So that'll be times E1, and maybe I'll put a minus sign in front, plus another LCM over an LCM E2. I'm not writing it out. Okay, I'll write it out in a minute. Okay, so essentially we're going to be dividing by GCDs, but as you continue the resolution, it's easier to express as LCMs. Okay, so now I will tell you the Taylor resolution. That was all just motivation. It's okay if some parts didn't make sense, because now I'm just going to do the definition from scratch. All right. I have no idea what time it is. Oh yeah, 15 minutes. Okay. All right, I have almost nothing left to say. This will take me 5 minutes. In general, here's what you do. Okay, so we start with a polynomial ring S. Okay, adjoin x1 through xn, any number of variables, and you start with a monomial ideal. So it is generated by some M1, M2, M, whatever you want, R. Okay, these are monomials. Means they're elements in the polynomial ring with no pluses and minuses. They're just single terms. Okay, you could have a number. Let's not put a number in front. It's a field, so divide, get rid of the number in front. So just monomials. For example, x squared and xy. Okay, then let's do exactly what we would do for the Kazoo complex, but change it a little bit. Okay, so let's take a free module of that same rank, s to the r. So that's a free module with the same thing, same number of generators as this thing, as the ideal. So with basis E1 up to ER. And the Kazoo complex on these monomials would be like sending E1 to M1, E2 to M2, and then a complicated formula what to send products to. Okay, so we're going to do that. Stop me if you have a question. Yeah, you don't have to start with a minimal generating set. Yeah, but you might as well. Oh no, like we start with x squared and xy, we will divide by g. Oh, I see. It will be, if you don't start with a minimal generating set, you will get ones, and it'll be non-minimal, and then that's okay. But this one might also be non-minimal, actually. Yeah, any list. It doesn't have to be a minimal set of generators. The Taylor resolution is a modification of the Kazul complex so the Kazul complex on those monomials. So K, we would have written this in the problem set as some list of elements. I just had like F and G, but you could put more elements, M1. So you, Kazul complex on these monomials. And I guess it's on the ring S. It's a semicolon. Okay. So it's the Kazul complex on these monomials, but we're going to change. So it's got the same free modules, but we'll change the differential a bit by some LCM magic. So with the same free modules, free S modules, I think I want to leave that. So I'm just giving the definition. I'm not doing an example because that is what you will do in Thursday's problem session. So I'm almost done. So T for the Taylor, I usually call it T instead of F for the Taylor resolution. So it's the following complex. 0 goes to wedge R of this free module F. It's the free module of rank S. And so on. Wedge 2F. Wedge 1F, these are the exterior powers of F. Wedge 0F and to 0, but I mean, maybe you want to write what it's resolving. So S mod I to 0. This is the part, that's not the resolution, that's the module we're resolving. And this map is epsilon, and sometimes I cut it off, so I can just talk about the resolution. Okay, so before I tell you the differential, let's remember what these exterior powers are for the people who are just learning about exterior powers. The 0th exterior power is the product of the empty set of E's of basis elements. So no product. The no product monomial is 1. It's to the 0th power, like x. E1 to the 0, E2 to the 0. Just think of it as 1. Okay, so this is really, S times the basis element 1. Okay, and the first exterior power of any free module is just the free module itself. It's just you not multiplying just one factor together, so just one E. So it's the direct sum of all these S, E, I's. So in other words, it's overall I, E1 through ER. It's the free module on the E, on the E's. Okay, and then wedge 2, you're supposed to take pairs. So this is the free module, direct sum of S, over all EI, EJ, where I is less than J. So you saw that on the problem set. It was products of variables where you put the subscripts in order. On the sheet, I said A1 is less than I2 is less than I3, but I'm just putting an I and a J because I'm too lazy. Could put I1, I2. Okay, and so on. All right, so this is what this looks like. That would be the Kazul complex. Now, I'll give you the differential. And it's almost the Kazul differential divided by a little bit of something GCD-ness. Well, modified. so in some sense, when you do these problems, you're also practicing the Kazoo complex, but you're modifying the coefficient in front a lot. So with differential. Okay, so I'm going to do some notation to make it easier to say. So if for any oh, that's not an ideal, that's a subset of the numbers from 1 to, what am I up to, R? Okay, instead of writing, we will write EI. So write EI for E. Well, oh shoot, I meant to say what the subset was. This subset, let's call it I1 is less than I2 is less than up to less than IP. So some subset. Then we write E capital I for EI1 times EI2 times EIP. Instead of writing all these products, I just gather up the set of subscripts and make it a set. So this I is a set of the indices, that's all. That's shorthand. And M sub I is going to come from the corresponding monomials, but I'm going to do something to them. So leave a blank, and you're going to do it to the monomials MI1, comma, 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 MIP. And what are you going to do to them? Calculate LCM. Okay, I still haven't told you the differential. This is notation. So the differential do you have any question about the notation? It's just shorter way to write the product, and then that's the LCM means least common multiple. Okay. So then we define the boundary of. Now, what do I need to find the boundary of? I need to. Oh, yes. Okay. I know. So this one is an ideal. I know. I know. It's just that if I have eyes, I want to call it an eye. I don't know what to do. I'm sorry. It's the I is the problem. Yeah, you could change the ideal. Okay. But then I don't know where I started because it's not on the board anymore. Yeah, that was the ideal there. Yeah. We should have called the ideal something else. Okay, I'm going to leave it. Okay, just because I don't want to fiddle with it all. So E sub I, and the bound, oh, right. So what do we want to define the differentials? You need to take a basis element in each spot and explain what the differential is. That'll give you the map of free modules. So what does a basis element look like? A product of EIs. Okay, so that's what we're calling E sub capital I. That's a product of EIs, and I just want to know where it goes under the differential. So it's the sum, K equals 1 to P. So again, this EI is standing for EI1 times EIP. There are P things here. So I'm going to go and remove one of these guys at a time, just like for the Kazoo complex, but leave a big space here. So I'm going to take EI1 ... and then the kth one, EIK, I put a hat on, I remove it up to EIR. So this one I remove. Okay. And if this were just the Kazoo complex on the EIs, on the M's, what would I put in place of the one I removed in front? I remove one. Yeah, the corresponding M. So MIK, I guess. No, MK, right, MK. So I would put an MK here. But I'm going to do stuff that divides out by GCDs. But it doesn't work so well dividing by GCDs. It works better to take an LCM. So I'm going to take an LCM of all the monomials that are involved all along here in the entire index set I, and divide by the LCM of the monomials if I remove I sub k. There should be a P here. Okay, so I'm going to cross it out and put a P there. So this should be I sub P. Sorry. Thank you. Next. Yes, this is called not looking at my notes. Right. Yes. So right here, there should be a -1 to the K plus 1. Thank you. Yes?
Your M sub I above is already an LCM.
Yes. So this is the LCM of all of them. This is the LCM of almost all of them. And so it has to be divisible. It might be 1 if these are equal.
It's an LCM of LCM.
Oh, MI is already an LCM.
Yeah.
Okay. Cross out LCM. Great. I don't work with a Taylor complex very much, as you can tell. Okay, yes, there's no LCM. So every source you look at uses different notation. And I think I combined several notations. But you could still do the LCM and we get the same answer. Okay. Good. So that's the LCM of all of them, and on the bottom I have the LCM of almost all of them, not the kth one, right? And I forgot the sign here. There should be a -1 to the K plus 1 in front of each term. Good. Theorem. This goes way back to Diana Taylor, who was a student of Hogster in 1966, proved this, that this is exact. So T is an S-free resolution of, can I write S mod I? Okay. Sorry, of whatever ideal, the ideal given by the monomials. Ah, why don't I just write the ideal of the monomials? M1 to MR. Okay. So it's just like the, oh yes, and I want to say one more thing. It's just like the Gazoo complex, but the thing in front is instead the LCM of all the monomials in that particular subset list divided by all the monomials except the one who's corresponding to the E you're removing. If you know what a DG algebra is, this might be interesting to you. Gameda proved in 76, and then it was reproved by Froberg, who might not have seen Gameda's paper, because Gameda's thing was in a thesis, so not everybody back then, there was no internet, okay? I came from that time. There's a kind of a product you can define on this resolution that makes it what's called a DG algebra, a differential graded algebra. So there exists a chain map, it means a map of complexes from T tensor T. Now you probably don't know, might not know what a tensor product of complexes is. S to T, which is giving you like a way to multiply things. You have two things. You look at the map, it tells you how to multiply them. So I'll put M2 here for, no, I won't put M2. I'll put mu for multiplying, making the direct sum of all these TIs and an algebra, an associative algebra, not commutative. And it's a very short and simple thing. It's if you know what a DG algebra is, you might want to know what it is. E sub I, which is a whole set of indices, times E sub J is the GCD of MI, that's an LCM, and MJ, that's an LCM, times EI, times the, like what EI times EJ. So maybe I should put a dot here. EI dot EJ, the definition of the product, is this multiplication is just happening in the exterior algebra. So if they share a common EI, the product is 0. If not, then it's not. If you don't know what that is, don't worry. But this is a very pretty resolution is the point I'm making. Yes? That's a really good question. I don't know all the answers to it. I know some equivalent conditions. Maybe this one is equivalent. So his question was, where's the there? When is this a minimal resolution? So what you want is all the coefficients to be in the maximal ideal. So you want all these LCMs over these LCMs to be not units, but in the maximal ideal. So that has something to do with that the monomials in a list have to have something in them that's not in the monomials if you remove something. But there are also powers to worry about, so there's a bit more subtle than that. So one sufficient condition would be if every monomial has a variable in it that doesn't show up in the other monomials. But I don't think it's equivalent because it's equivalent for square free, but it's not equivalent in general. There are equivalent ones, but they're kind of messy. It's very often not minimal. Yeah, it's not, yes. It's very often non-minimal. And my students, together with Hugh Geller, so Henry Potts-Rubin, Des Martin and Hugh Geller proved that if you start with the edge ideal of a tree, it has a DG algebra. Well, okay. And then the edge ideal of the tree's minimal resolution has a DG algebra structure if and only if the tree is smaller than width 5. But it's not always the Taylor resolution is the problem, so it's very hard to show. So very in that case also Taylor resolution is not minimal. Yeah. Oh, because you can't, when they're monomials, this you can divide. But if you're, I mean, if you're given some polynomials, what do you mean by LCM and what do you mean? And then it's true, but an LCM will very often, if you run a bunch of polynomials like x squared plus xy, y cubed minus z plus 4x squared, they'll very often, LCM will just be the product. I can't think of what to say right now. Yeah, it just becomes the Kazoo complexity then. But I don't know if their LCMs are different. If yeah, I mean, if they're not a regular sequence, that's kind of a problem. It's not going to be exact. Yeah. So there are still questions about can you lift this to, if this is the initial ideal sign, can you construct a similar resolution for the non-monomial thing before you took the initial ideal? Yeah.
Thank you.
Okay. Thanks.